This is a penny, and soon their use in the US will go extinct. So some stores like Aldi and ShopRite are already phasing out the use of the penny, and they're coming up with systems to deal with that. But the question is, are systems like this actually fair to the customer and the store? This is what we want to mathematically analyze.
$56 million a year.
We're not getting rid of the penny. We're discontinuing the production of it.
Though for some businesses, not making sense doesn't make sense. Some retailers are already seeing penny shortages and trying to figure out how to handle cash payments, which make up 17% of all transactions at Quick Trip convenience stores.
Here at Quick Trip, for the favor of our customers, we decided to round down for every transaction. That will cost us this year $3 million.
How do you feel about that?
Well, we wish there was a better option, but we have to do it for the sake of our customers. We didn't want to cheat them out of a single penny.
Would the stores actually be cheating the customers out of a lot of money? And perhaps there is a better way. What about that system in ShopRite? This is why we need to learn how to think critically. This is why we need to do mathematics properly in school. I mean, $3 million is a lot of money. So perhaps there's a better way for it to be fair for the customer and fair for the store without losing all that money. So what's the worst case scenario? The worst case scenario for the store is to lose millions. But what's the worst case scenario for the customer? In order to answer this question, we need only look at the last digit of the change, otherwise known as the pennies digit. So you can analyze each case and look at how many pennies come from each digit. And if you do that, you see that 4 and 9 produce the most amount of pennies. They each produce 4 pennies. Say your grocery bill is $98.11, which is all too common nowadays, and you hand the cashier a $100 bill. Then you get back $1.89 in change. So let's say you go to the store and you get back $1.89 in change. Now all that matters is the digit here. So how do you give back 9 cents? Well, you have 4 pennies. And you have 1 nickel. 5 plus 4 equals 9 cents. Now the thing is, since the stores are not carrying the pennies anymore, you're not going to get 4 cents back. So you'll lose 4 cents in one shopping trip. So that's the worst case scenario. That's the maximum you can lose. Let's do a calculation to try to put this into perspective. Say you make an average of 1 grocery trip per week. Since there are 52 weeks in a year, worst case scenario, you lose 4 cents a week times 52 weeks equals only $2.08 per year. Alright, so to even begin to argue why the penny scheme is fair, we first need to go over some basic probability. So for the case of a discrete finite number of events, we have that the probability of an event X occurring is the number of favorable outcomes divided by the total number of equally likely outcomes. And associated with any probability space is something called the sample space. The sample space is quite simply the set of all possible outcomes, or the list of all possible outcomes. So X will represent the event of getting one of the 10 digits 0 through 9 on the last digit of the total of your grocery receipt. So how do we find the cardinality of the sample space, or the number of elements, or numbers in the set? Well, we could just count 1, 2, 3, 4, 5, and so on. But what if there's thousands or millions of numbers? How can we quickly find out how many elements are in the set if it's an ordered list like that? Well, we have to know basic combinatorics. And here's a great book by Ivan Neven, The Mathematics of Choice, The Art of Counting Without Counting. So it's just the last number minus the first number plus 1. So 9 minus 0 plus 1. If the list of numbers only differs by 1. So let's do a quick example. What's the probability of getting a 2 as the last digit in your receipt? Well, there's only one favorable outcome, which is 2. And there's 10 total possible equally likely outcomes. So that's 1 divided by 10, or 10%. There's a 10% chance of getting a 2 as the last digit. Now, of course, the same logic holds for any of the numbers in the sample space. So the probability of getting any of the digits is the same, 1/10 or 10%. All right, so now here's the key idea for the crux of our argument for why the penny scheme given by these stores like ShopRite should be fair.